Okay, as I said, or as I announced on Blackboard, I'm gonna supplement the weekly lectures with a few with a supplemental lecture. And hopefully I don't have to do this the rest of the semester, but somehow we got behind and I'm not entirely sure how. I think it might be due to the fact that we do have bi-weekly lectures and that's less time than having 3 lectures a week. Um, but anyways, so in this lecture, we're going to cover section 28. So let me share my screen. Hopefully you can see. Hold on. Oops. All right. Hopefully you can see what I'm seeing. All right. So we're going to go to, we're going to work in 2.8. This is on injective. Oh, this is very laggy for some reason. This is on injective functions. In injective functions and inverses. The book calls these one-to-one functions, but I prefer the term injective. So first of all, let's just recall the definition of a function. So let me get this definition up. So, and just remember some key properties of a function before we can talk about what an injective function is. So it's going to be a type of function. So a function, recall, denoted by f, is a rule assigning to each element x in some set A exactly one element um, called f of x. So it's the result of applying f to x in a set B. So you take a point in A, you apply f, it's some rule, maybe it's squaring, maybe it's cubing, whatever, it doesn't really matter. You call the output f of x, and that's the output is going to be in set A. So we typically use this notation to indicate that f is a function from A to B. A is going to be called the domain. Oops. Of f, and then B is called the codomain of f, although that term doesn't come up as much. All right, so and then you can talk about the range of a function and different that you can. And then last time we looked at adding functions, multiplying functions, dividing functions, and the last thing we looked at was composition. All right, let me write that as a definition. This is gonna be important for when we define um, injective functions. So recall, what does it mean to compose two functions? Let's recall that. Okay, so um, given, say f goes from A to B, oops, doesn't seem like my microphone's picking up anything. Hold on. I don't know. Hopefully yeah, okay, now I see it works. Okay. Anyways, so given a function from A to B, and then given a function, let's say from C to A, or no, I'm gotta be careful about this. A to B, and then I guess, okay, so then G will go from B to C. So given, and these are gonna be functions, the composition of F and G, and we'll say it's denoted by F composed G, so that's how you read this symbol right here. F composed with G, oops. Now that's going to be a function from, let's see, did I do this right? No, I did not. I didn't do the domains right. Let's see, so at G, we want the output of G to land here. Okay, so it's going to go from C to A. So G takes something in C and it sends something to something in A, and then F is going to take that thing in A and send it to B. So what this is going to be a function from is C to B. It's like you're going to kind of pass through A. So you have this function F composed G. It's a function from C to B, and it's defined as follows. So I get a in order to define a function, I need to know the domain and the codomain, and then the rule. So how does the rule define? Well, it's defined as follows. It's exactly what I said in words. Basically, you take your input X, you feed it through G, that gives you G of X, and now G of X is a point in A, and A is the domain of F, so it's something you can plug into. Remember, domain is the set of allowed values that you're allowed to plug into a function. So G of X is an allowed value, so you can plug that into F of X. So this gives you the composition. All right, so now with that in mind, let's look at one-to-one functions. So the idea of a one-to-one function is pretty simple. Basically, the idea is that any 2 points um, in the domain have distinct outputs. There's no 2 points that get sent. There are no two distinct points in the domain that gets sent to the same point in the codomain. So let's try to formalize that and mathematically. So that's the rough idea behind an injective, or the book calls it one to one. I prefer the term injective though. So a function, say f from A to B, and again, A, B, we're always going to take A and B to be sets of real numbers. So just you can think of this as a function from R to R if you'd like. So as we say that it's injective, uh, if no two elements, so I'm just writing down what I said in words. If no two elements in A have the same image under F, and that is to say more precisely, that is, now this is the important part of the definition, is trying to formalize that condition. Basically, f of x1 is not equal to f of x2 whenever x1 is not x2 in A. So x1 and x2 are points in A, but they're distinct. And so whenever you have two such distinct points, their outputs better be distinct also. So they no 2 points get sent to the same um point. So this condition right here can be equivalently phrased. This is just a point of logic, not a mathematics anymore. So logically, this statement right here is equivalent to the following. If f of x1 is equal to f of x2, then so assuming you have an injective function, that is this condition right here holds. If you have an injective function and you apply to x1 and x2 and you get the same output, the only way that can happen is if x1 and x2 are the same. That's the only way that can happen. So this is a very strong condition on the function. Um, so from this, we actually get, if we're thinking about real valued functions, real functions, which is basically all we're going to think about, functions from the real numbers to the real numbers. This actually immediately gives us the so-called horizontal line test. Um, and it's going to be, we've seen something like this, but it's going to be phrased differently now. So horizontal line test. We saw like a, for example, a vertical line test, but now we have this horizontal line test, and maybe you've seen something like this before, but it's going to be phrased slightly differently. So it gives us condition necessary and sufficient conditions for when a function is injective. So a function is inject according to this criteria, a function is injective if and only if no horizontal line. So now we're talking about instead of talking about vertical lines, we're talking about horizontal line. No horizontal line intersects its graph more than once. So why is this? Let's think about why this is true. So like, let's suppose I draw. Oops. Uh, see if I can figure out how to do this. Changed one note on me, so I'm not exactly sure. Maybe shapes. All right. So let's try to understand this. Let's try to understand this criteria a bit. So let's just draw a generic function. Uh, let's draw a non-injective function, okay? Function which is not injective. So if you're non-injective, that means, what does that mean? Let's say, all right, let me back up a little bit. Let's try to justify this criteria. So let's say, suppose F is not injective, okay? So we don't satisfy the definition of injectivity. What we're trying to do is we're trying to justify the horizontal line test. So I can't use the horizontal line test to justify itself. That would be circular. So let's go back to the definition. So what does it mean to be non-injective? Well, if you look at this, you stare at the definition alone of to be non-injective means that there exists a pair of points that are distinct, but their outputs are the same. So non-injective means there exists, say, x1 and x2 in your domain with x1 not equal to x2, but so these are distinct points, but they have the same output. And we've actually seen lots of functions like this. We've seen both. We've seen injective functions and functions which are not injective. Um, so how can we visualize this? So maybe like there exists maybe x1 and x1 2 are here, okay? And then there exists these points and they're at the same height because remember, I'm going to eventually draw the graph of function. But what is if you have distinct points x1 and x2 and but they have the same output, that means that they have to be at the same height from the x-axis. That's what the f of x tells you. It's the y coordinates, the output. So basically, maybe the graph looks something like this, and you just fill in the rest. All we care about are these 2 points being the same, and then maybe it looks like this, and then it goes up. Who cares? It doesn't really matter. The point is, though, that because these 2 points are the same graph, you can draw a a horizontal line through them. In fact, according to the example I drew, this just this arbitrary generic example, it intersects 3 points at 3 points, but all we care about are these 2 points, at least 2 points that have the same output. So if you're not injective, that means you can find a horizontal line intersecting the graph more than once. So it's not, in other words, this fails to be injective. And this works both ways. So if you're not injective, suppose you're not injective, okay? Then you get these 2 points, x1 and x2, that they're distinct, but they have the same outputs. That means you can draw your graph like this, and so this would verify the horizontal line test. Now, conversely, suppose I give you a graph like this, and there's a horizontal line that intersects at 2 points. We want to conclude it's injective, but it's clearly injective because if this horizontal line intersects at two distinct points, that means you can find x1 and x2. And since if this is a horizontal line, the y coordinate is the same, right? When you look at a horizontal line, the y coordinate is constant. But these 2 points are, this right here is f of x1 and f of x2. And if they lie on a horizontal line, that means they have to be equal, right? So this proves that if you can find 2 points where this happens, then you can actually, sorry, if you have a graph where you have this horizontal line passing through like this, then that's going to imply that your function is non-injective. So this works both ways. If you're injective, then you can find 2 points, x1 and x2, with the same output, and that allows you to construct this horizontal line. That's one direction of proving the horizontal line test. The other direction is this: suppose you have such a horizontal line, and if you have such a horizontal line, it has to just intersect the curve at two distinct points. Call them x1 and x2. You can call them whatever you want; it doesn't matter. But you have these 2 points, x1 and x2, and since these points right here on the curve also lie on the same horizontal line, they have to be equal because remember, as I said, the y coordinate, the output is the same. It's constant on a horizontal line. So that's why we have this horizontal line test. That's why this is true. All right, so let's try to decide whether um some functions are one or not. Okay, so I feel like I taught this already, but I don't think I did. No. Anyways, so let's suppose we have f of x, and it goes from r to r, and it's defined by f of x is equal to x cubed. Well, we can actually justify this in a couple ways. So sorry, what is the question? Or let's say it's a claim. Show this is going to be injective. It's going to be injective. So there are going to be a couple ways you can verify that. That's what I was trying to say. Sorry. So let's show this is injective. So the first way, there's a couple ways. First way, or maybe I won't use a dot. Let's say first way. So the first way is just to go back to the definition. Um, use the definition to prove that it's injective by definition. So I'm going to use this right here. So how do I prove injective? Well, I'm going to assume this. I'm going to assume that f of x1 is equal to f of x2, and then I'm going to conclude that x1 is equal to x2. And that will prove that this is injective. So here's the first way. So let x1 and x2 be real numbers. I'm not necessarily assuming they're the same or they're distinct. They're just they're just two x1 and x2 are real numbers, possibly the same, possibly not. I'm going to conclude that they're the same though. So we're going to say let x1 and x2 be real numbers such that f of x1 is equal to x2. So this is my hypothesis. I need to assume that, and then now I want to conclude that x1 and x2 have to be the same. Well, what does this condition right here mean? Well, go to the definition of f of x. It's x cubed right here. So you're cubing it. So f of x1 is going to be x1 cubed, and that's going to be equal to x2 cubed. But I can take the cube root, right? And I don't have to worry about pluses or minuses because I'm taking an odd root, right? So this is going to be x1 is equal to x2. Check. So so we assume that f of x1 is equal to f of x2, and we were able to conclude that x1 equals x2. So this implies that f is injective. All right, so now the second way would be to use the horizontal line test. And to do that, you need to plot the function. Oops, no, that's not what I want. I don't know what I just did. Uh, maybe, yes, shapes, okay. So let's plot this function. All right, so remember, x cubed looks something like this. Let's see if I can draw this. Something like that. And you can see, I mean, this is not going to be as rigorous a proof because, you know, yeah, so this is the preferred method, this first way. This is a rigorous logical proof. There's no ambiguity, there's no doubt in it that it works. This one is not so much of a proof, it kind of gives you evidence that this is injective because, I mean, from here you can see that if I just intersect horizontal lines at random, it's just gonna intersect the curve at one spot. But how do I know? So here again, one spot. How do I know that if I don't go far enough down, like the graph of um how do I know if I don't go far enough down, this doesn't come back somewhere up over here? So like these geometric methods for proving things aren't as reliable because there's that doubt. Like it turns out that the function can't do that, and that's actually because of this proof right here. This first way I proved injectivity. It can't be true that this goes down and then it's super far out, way over off the screen. It kind of comes back up. That won't happen. Um, but there's not really any way of knowing because there are infinitely many numbers, and I mean, you can't go far enough out to verify that. But I mean, on this small portion of the graph, you can see it works. So this method shows you, yeah, this was probably injective. It's not as rigorous. Um, this is the better method. So, but we can say by horizontal line test. This would be a second method, not as rigorous. So horizontal line test, f of x equals x cubed is injective. All right. Now let's look at a second example. So, um, here's the next one. So let f be a function from R to R. with f of x is equal to x squared. So the question is f injective? So again, there could be two ways you see this, and they're kind of related actually. So let's get a plot of f of x, which is x squared. And it will be clear from this that it's not actually going to be injective. The answer is no, it's not injective. So you plot this function right here. The squaring function looks like something like this. And you can see, yeah, there are a lot of horizontal lines that intersect at more than one spot. In this case, it's actually always two spots. Any horizontal line or at most two spots, let's say, because this horizontal line doesn't intersect at all. But that's not the point of the horizontal line test. The horizontal line test is if you have at least one horizontal line that passes through 2 points, then you're right away not injective. So you can see it through the horizontal line test. But you can also just do a simple calculation. So f of -1 is going to be -1 squared, which is 1. And on the other hand, f of 1 is going to be 1 squared, which is 1. So -1 and 1 are distinct points, but they get sent to the same point. So f is not injective. Now, what about and these are two ways to see it. Now, what if we change domain? What if now the f of x is a function from 0 to infinity to the real numbers, and it's still the same rule. You square every number. Well, in this case, when you plot the function, you're not plotting everything over here. You're just plotting this portion right here. So if you draw any horizontal line, it's just going to intersect at one spot, right? So this should be injective. And it's not hard to prove it rigorously from the definition. So the answer is yes, and here's the proof. So you suppose x1 and x2 are in here such that f of x1 is equal to f of x2, okay? So now, if this is the case, then what you have is x1 squared is equal to x2 squared, okay? Now here, we're going to take a square root. We're going to kind of do what we did with the cubing. We're going to take the square root, and then technically you have, what you're going to have is x1, um, sorry, when you take the square root, let's actually be a little more careful. Okay. Um, yes. When you take this square root here, now when you take the square root of something squared, you technically should have an absolute value like this. So now this technically doesn't prove x1 is equal to x2. It just says the absolute value of x1 and x2 are equal. But here's the critical assumption. Don't forget what you're assuming. You're assuming that x1 and x2 are non-negative numbers. So that implies that the absolute value of x1 is just x1, and the absolute value of x2 is just x2. So this does in fact imply that x1 is equal to x2. And see this, you can see that this step breaks down if you don't assume this right here. So for example, if x1 and x2 are just any two random real numbers, and like we have up here, or when we had this function that was defined on the set of all real numbers, there are numbers with the same absolute value, namely -1 and -1. So at this step, if you didn't assume that every number was non-negative, you could have that the absolute values are the same, but this one hold right here. So for example, you could have -1 and 1, they have the same absolute value. But because x1 and x2 are non-negative numbers, they are equal to their own absolute value, and you can conclude this right here. So the point is, this is the point I'm trying to make here, is that when you talk about when you ask whether a function is injective or not, it's not a matter of just what is the rule, but what is the domain. So we're trying to really emphasize the fact that a function has two pieces to it. It has a domain, as the set on which it acts, and then there's the rule by which it acts. So these two pieces are critical. They're very important. You can't talk about a function without knowing the domain and the rule. You need both pieces. And depending upon, like, so you could take this same rule at the squaring, but consider different domains, and you suddenly go from being not injective to injective. So the question of whether a function is injective depends upon your domain and the rule. All right, let's see what else do we have. So, all right. So now let's talk about the inverse of a function. So now that we introduced injective or one-to-one functions, we talk about the inverse. So this is probably one of the more complicated and abstract things. So let's just go over this carefully. So the inverse. So inverses only make sense when you talk about injective functions, and it will be clear why that's the case from the definition of inverse, that it only makes sense for those functions. So we're going to just start off with talking about an injective function. So we're going to say we have a function from A to B, and this is, as I said, going to be an injective function, or one-to-one if you're reading the book. So injective function. And it turns out you can define associate the function to it, and it's called the inverse. So then it's inverse, and this function is unique. Its inverse function denoted by f to the -1. So I want to be clear that this is not an exponent, it's notation. It's not saying like you're taking something and raising it to the -1's power. That's not the case. This is just more notation. So now the inverse function is a function from not A to B, but B to A. The inverse function is going to be basically the function that undoes f. It just undoes the whatever f does. So I specified the domain and the codomain of f inverse. Now I have to tell you how it's defined. And is defined as follows. So what does it do to a given input? So the input is going to be y, and that's going to be in B, is equal to x if and only if f of x is equal to f of y. Or sorry, f of x is equal to y. So this might look confusing because it's not saying like, oh, f is just x squared, x cubed, or whatever. What is the rule actually telling us? Well, here's how it works. I give you a y, which is in the domain of f, right? In f inverse, the inverse function. I want to know, what does it do to a given y? What does it do to a given input? Well, it sends it to some number x. We don't know what x is, okay? But whatever x is, it has to be that number such that this holds. So basically, I give you y, you want to know what it does to x, or sorry, I give you input y, you want to know what f inverse does to it. Call whatever it does x, And then x has to be that number such that this equation holds. So to find out what y is, you have to solve this equation, and then that's going to be the number that's going to tell you what f inverse does to a given input y. So let's look at an example. Okay, maybe that will clear things up. So this is example 4. So I'm not gonna actually define this whole function. Actually, let me make a note before I go through this example. So as I said, f of y, or let me say note, f inverse of y does not equal 1 over f of y. This right here is not an exponent. It's notation. It literally just denotes the inverse function if it exists. Sometimes it doesn't exist. If your function is not injective, it won't exist. So for example, f of x equals x squared as a function from R to R is not going to have an inverse function. So so this is, yeah, just want to emphasize that that's not an exponent. All right, so now let's go through example 4. So we're gonna suppose I give you a function, and I'm telling you that f of sends 1 to 5. It sends 3 to 7, and it sends 8 to -10. What Given that, what are I should also say, suppose this and f is injective, right? Because we're going to talk about the inverse function, and you can only have an inverse if you're injective. So what are f inverse of 5, f inverse of 7, and f inverse of -10? Sorry, and f inverse of -10. Well, let's just think about this one first. Remember, um, f inverse sends some input y equals 5 to some output x if and only if f of x, if and only if f satisfies this equation, right? All right, so basically we're asking, what does f inverse do to the input 5? Well, I don't know what it does, but call it x. And whatever x is, it has to be such that this condition right here holds. So what we need to ask ourselves is, what number does f send to 5? Well, we're told that f sends 1 to 5. So we can say, well, f of 1 is equal to 5. So that implies that x has to be 1. But if x is equal to 1, then f inverse of 5 is equal to 1. So that's how you use the definition of an inverse function. Figure out what does the inverse function do to a given input. Let's do one more. We won't do the other one, but we'll just do f inverse of 7. So f inverse of 7, well, we want to know, what does f inverse do to 7? Well, we don't know what does at the moment, so let's just call it x. Now, by definition, the inverse, whatever x is, it has to satisfy this equation. F of x is equal to 7. So again, we have to ask ourselves, what number does f send to 7? Well, we're given that. It's up here. We're told that f sends 3 to 7. So that's going to imply x is equal to 3. But if x is equal to 3, then that means f of inverse of 7 is 3. And so that allowed us to determine what f inverse does to the input 7. All right, so that's enough for that. I think let's see, what else do we have? For that example, we won't do the last part. So it turns out you might be wondering why I introduced or why I recalled the definition of a composition of functions. And that's gonna be because of this next property I want to introduce. So there's another way, and maybe a more straightforward way of thinking about inverse functions, and in fact determining the inverse function. So inverse function property. This is a property of inverse functions. This actually uniquely characterizes inverses. So the setup is as follows. You take f to be a function from a to b. Let's say it's not just any function, but let f be an injective function. Then the inverse, f inverse, which is a function from b to a, is that unique function. This is important. It's unique. It's the only function that's going to satisfy the following two properties. Function, so that unique function satisfying the following cancellation properties. So we have f inverse composed with f of x is equal to x, and that's for all x in A. So notice what this is one condition. There's going to be another similar condition. This basically, what does it do? It says it undoes the inverse function undoes whatever f does. So you plug x into f, it does something. We don't know exactly what it does, but whatever it does is it's such that if you apply f inverse, it's going to undo it to just give you back x. So this is actually what's called the identity function. It's the function which sends a point to itself. It doesn't transform the point in any way. It's not like going to square it or cube it or multiply it by 5. It just sends a point to itself. So if you let f act on x and then the inverse act on that, it's the same as doing nothing to the point at all. It just moved it around in the space and then it landed back at the same spot, basically. And the other property is it's the composition in the reverse order. So you apply x, you apply f inverse to x and then f to the result, and it doesn't do anything. It just sends the point to itself. And that's going to be for all x now in B, because B is the domain of f inverse. A is the domain of f. So this literally does say that f and f inverse undo each other. They undo each other. And f inverse is the unique function that has this property. If you find a function g such that g composed f of x equals x, or g f composed g of x is equal to x, no matter which way you compose them, then G just has to be the inverse. So this gives you a way of finding the inverse, like a way of maybe guessing what the inverse is going to be. So here is an example of doing just that. So for this one, we want to show or verify that f of x is equal to x cubed and g of x equal to x to the 1/3 are inverses. Well, we just got to compose the two in both order and show that they undo each other. So let's do f composed of g of x. That's going to be f of x to the 1/3, because that's what g of x is defined to be. And what does f do? It cubes it. So it's going to be x to the 1/3 cubed. The 1/3 and the cube, they're going to cancel to give you x. So look at f composed g takes a point x and sends it to x. So it doesn't, they undo each other in that direction. What about the other direction, or the other composition? So let's verify that. So f of x is defined to be x cubed, and then g is defined to be the cube root of it. So you take x cubed to the 1/3. And now the 3 and the 1/3 are going to cancel to give you x. So g composed f takes x and sends it to x. And then what you can say is, so this does show that they aren't inverses. And then by uniqueness, you can say that g is equal to f inverse. G is going to be the inverse function. All right, so here's another example I'm going to add in. I don't think the book does it. All right. Anyways, yeah, I don't think the book does it. So I'm going to add this in. So let's take f to be the function and try to figure out the answer based on the calculations we did. So f is going to be the function from 0 to infinity, and it takes x to x squared, right? So no, we showed that f is injective, remember? And that's because of this domain. If f were defined on all the real numbers, then this wouldn't be injective. But since it's defined on 0 to infinity, f is injective. So now the question is, what is the inverse? So maybe pause it for a second and try to figure that out, and try to like mimic these kind of calculations to maybe figure out what the inverse would be. All right, so if you paused it, let's do this together and figure this out. So notice you have x cubed, that's f of x. What did you need the outside function, the g function, to be in order to cancel that cube? You would need it to be the third root. So it's going to be the root. So here's the claim. We claim f inverse is equal to square root of x, which is also the same thing as x to the 1/2. So let's verify that. So actually, let me be a little more precise. Oh yeah, no. This is fine actually. So yeah, it's injective. So the function f is injective, so it has an inverse. And now the question is, what is the inverse? So f inverse of x, let's calculate that and show that it equals x. So f inverse is going to be the square root of x. And then this is going to be square root of x squared. And so those are going to cancel to give you x. What about the other direction? So it's going to be f inverse of x squared, because that's what f of x is. And then f inverse is the square root, so it's going to be square root of x squared. Now this is going to be absolute value of x technically, but what's the domain? It's non-negative numbers. So absolute value of x, absolute value of a non-negative number is the number itself. It's x, and so absolute value of x is x because x is non-negative. So this implies f inverse of x equals square root of x is in fact the inverse, because it satisfies those two cancellation properties, and those uniquely characterize the inverse. All right, so this is more or less just like guess and check, and sometimes it's not always easy to guess the inverse of a function. So now I'm going to outline a procedure on finding the inverse of a function that works somewhat more generally. Now guessing is perfectly fine, honestly. As long as you show that the whatever you're guessing, whatever you guess to be the inverse has the property of being the inverse, then you've shown it has an inverse and you've shown what the inverse is. And that's a perfectly legitimate way to do it, to just guess. You have to verify, you have to justify your guess. Um, but here's a more like algorithmic way of finding the inverse. So finding the inverse. So there's three steps to finding the inverse. So the first step is this. What you're gonna do is you're gonna write y is equal to f of x. So set up this equation. Now, what you're gonna do is you're gonna interchange x and y. You're gonna swap them. And this is because you want this inverse. You remember, what does the inverse do? It undoes each other. So it's like it's almost like you're swapping things around. And then you're gonna swap back. Now, since you swap for them, you have to swap them back. But first, you're gonna interchange them and then solve for sorry. So you're gonna interchange. The book's actually doing it a little differently, which is kind of screwing my head. Um, so I just realized, yeah, the book does it differently. Oh yeah, okay, I see. I see. I'm sorry. So, anyways, they do state it the way I state it also. They state it two different ways. So I'm gonna just continue with stating it the way I'm stating it right now. So we're gonna interchange x and y and then solve for y in terms of x. And then once you've done that, now the resulting once you've done that, the resulting equation is y is equal to f inverse of x, and that will give you the inverse. You'll actually have the inverse. You have y is equal to some expression in terms of x, and that will you'll be able to read off the inverse. So those are the three steps, and let's see how do we use these three steps to find the inverse. So suppose I give you f is a function from R to R, and this is going to be f of x is equal to 3x minus 2. So this is a line, a non-horizontal line. If you plot it, so it implies that f is injective, right? It satisfies. If you have a non-horizontal line, it's like angled at some way, then it satisfies the horizontal line test, right? So if you don't see that, try writing that down. Draw a non-horizontal line and show that it satisfies the horizontal line test. And so because of that, it's injective. So now let's go through the steps. So what is the steps? We're gonna write y is equal to f of x, but f of x is equal to 3x minus 2. So we have this equation y is equal to 3x minus 2. Now we're gonna switch x and y. So we're gonna get x is equal to 3y minus 2. So this is the first step. Here's the second step, and now we're gonna do the third step and solve for y. So we're gonna get 3y is equal to x plus 2. So I added 2 to both equations and I just rotate the equation. And now I can divide by 3. So I get x plus 2 divided by 3. And this right here is going to be the inverse. So this implies that f inverse of x is equal to x plus 2 over 3. So does this actually give us the inverse? Let's actually verify that. So f inverse of x is equal to f of x plus 2 over 3. Let's verify that they actually do undo each other. So now f of x is 3x minus 2. So it's going to evaluate this, it's going to be 3 times x plus 2 over 3 minus 2, right? So remember what f of x does. It multiplies 3 times your input and then subtracts 2. Our input is x plus 2 over 3. So 3 times that, um, minus 2. So now the 3's cancel, you get x plus 2, and then minus 2, and then you get x. So that's check. That verifies the one cancellation property. I won't do the other calculation, but similar. So I'll just write that down. Other calculation similar. Actually, let me just say f inverse of f of x is equal to x is similar. Verifying this is similar. So I won't go through that. All right, let's see. Um, so there's a couple more examples. I think they're pretty good, so we should go through them together. So this is example 8. So we have f of x is equal to x to the 5th minus 3 over 2. And this is going to be an injective. So what we want to do is find the inverse. So we're going to set y is equal to f of x, which is x minus 3 over 2. Now we're going to swap x and y. So we're going to get x is equal to y to the 5th minus 3 over 2. And now we're going to solve for y in terms of x, and that will give us the inverse. So I'm going to rotate the equation and multiply by 2 to get this. And then I'm going to add 3 to both sides to get, so I get 2x plus 3. And now I'm going to, so it implies that, and then this is going to imply that y is equal to 2x plus 3, fifth root, the fifth root of that, the fifth root of 2x plus 3. And you can go through the same calculations here to verify that those composition or those cancellation properties hold for these functions. This is in fact the inverse. So f inverse of x is equal to 2x plus 3 to the 1/5. All right, so that's now let's do example 9. So example 9 is a rational function. So we have f of x is equal to 2x plus 3 over x minus 1. So the first step is set y equal to f of x. Well, that's going to be 2x plus 3 over x minus 1. And now we're going to swap x and y. So now we're going to have x is equal to 2y plus 3 over y minus 1. And then finally, we're going to solve for y. So I'm going to multiply both sides by y minus 1. So we're going to x times y minus 1 is equal to 2y plus 3. Now I'm going to distribute the x through to get x times y minus x is equal to 2y plus 3. Now I'm going to put the y terms together and factor and put everything else on the other side. So what I'll have is 2x plus y is equal to x plus 3. So it should be negative 2y here because I'm subtracting 2y. So I subtracted 2y and then I added the x to both sides. And now I'll factor the y out to get x minus 2 is equal to x plus 3. And now finally I divide by x minus 2 to get following. So this implies that f inverse of x is equal to x plus 3 over x minus 2. And again, you can verify that this function satisfies that cancellation property. And it would be a good idea, honestly. I'm not gonna go do it for the sake of time. But you should go through that because those are good exercises to practice your ability to do algebra and arithmetic and do some manipulations. So you can see everything we've learned really just builds stepwise to some more advanced and abstract topics. So all those things we learned at the beginning of the semester are all crucial. All right, so that's that. And so the last thing I want to talk about is just I'm actually gonna pull up the book now because I'm not gonna even attempt to draw these graphs. But here's a graphical way of looking at um the inverse of a function. So let's just read this together. So um principle of interchanging x and y to find the inverse also gives us a method for obtaining the graph of f inverse from the graph of f. So here's the point. If f of a is equal to f of b, then by definition, remember call the definition of inverse. That's the case if and only if f inverse of b is equal to a. Remember, they have to undo each other. They do the opposite of thing. So if f sends a to b, f inverse is going to send b to a. So what does that mean? It means that AB is a point on the graph of F if and only if the reflected point BA is a point on the graph of F inverse, right? Because F sends A to B, that means the point A comma B is a point on the graph of F. And if F sends A to B, F inverse sends B to A, which means that B comma A is a point on the graph of F inverse. So what does that mean geometrically? So it means that the graph of F inverse is obtained by reflecting the graph of F across the line y is equal to x, this diagonal line. So you have this diagonal line right here. Here's a point A comma B. The point B comma A is reflected. You can see it's reflected over um, the graph. And if you're not sure, just take specific numbers like 1 comma 2 and plot that point. You'll see that 2 comma 1 is going to be a point reflected over the graph like we have in this diagram right here. So play around with some numbers if you have to see that the point A comma B and B comma A really are reflections of each other over this line. So now if you have the curve in blue and you know it's injective, and you can see that because it satisfies the horizontal line test, it has an inverse, and the inverse is going to be the reflection over the diagonal line, basically because of this paragraph right here. So read this if you don't fully understand that, just give this paragraph a read a couple times, play around with some numbers, and just think about it, and then take a break and then think about it tomorrow. That's really how mathematics is done. It's not something you can just look at and understand immediately. You just gotta think about it for 5 minutes here and there, and then take a break and work on something else. All right, so I don't know if these are really interesting examples, I guess. So you have the graph of f of x is equal to x minus 2 squared. So remember, the square root function starts at the origin and opens up like a half a parabola rotated. So because you're subtracting 2, that means shift over to the right 2 units, right? Remember? This is a horizontal shift to the right when you subtract the 2 like that. So we want to know what is the inverse, so the graph of it, and then actually find an equation for it. So the graph of it by this discussion up here is going to be just a reflection of it over this diagonal line. So it's going to open up like this, and it's going to look like a parabola, and in fact, it's going to be a parabola. So blue curve is the function you start with. It's invertible. It has an inverse. So reflect it over the line like so to get the red curve, which is the inverse function. So what is the inverse function? What does it actually look like? So we can kind of verify that the red graph is the correct graph. Well, let's go through those 3 steps to find the inverse. So how do you do that? You set y equal to the function, so it's x square root of x minus 2. You swap x and y, right? Then actually, let's see. Oh no, they do it. They do it. Okay, you can do the steps in different orders if you want. They set y equal to the function, then they solve for x. Okay, then they swap x and y. So it doesn't matter. You can do it either way. I prefer the way I've been doing it. So you can solve for x, and this is what you get, and then you interchange x and y to get the inverse. And look at that, it's a parabola. So, which is what you would expect the inverse of the square root function to be, of some sort of parabola, x squared function. And notice it's the right one. You have x squared plus 2, which means you take the parabola and you shift it up 2 units, which is exactly what we have. We only have half of the parabola though, because of this step right here. A y squared plus 2 is going to be a non-negative number. It's, in fact, it's y squared plus 2 is always going to be greater than or equal to 2, because y is going to be greater than or equal to 0. And so that implies that x is going to be a positive number only, right? So we're only graphing half of the parabola, which makes sense. We don't want to graph the whole parabola because that's not an injective function. All right, I think that's it. That's enough. We definitely covered a lot, and I think this is going to help doing an occasional virtual lecture like this. I know it's unfortunate that we had to do this, but this is the only way to get through the material. So